our solar system is missing a planet. Not a dwarf planet, not an asteroid, a giant world. Scientists can account for Jupiter, Saturn, Uranus, Neptune, but when they run simulations of how those planets formed and settled into their present orbits, an unexpected pattern keeps appearing. The numbers work better when there are five. Again and again, the same story emerges: a young solar system crowded with giant planets, a period of instability, close gravitational encounters, and then one of those worlds is thrown away, not destroyed, not swallowed by the sun, ejected, cast completely out of the solar system into the darkness between the stars. If that planet existed, it may have been similar to Neptune, an ice giant with a thick atmosphere, powerful storms, and a mass many times greater than Earth's. For hundreds of millions of years, it would have been one of the dominant worlds orbiting our sun. Then it vanished. Some researchers believe the event that removed it reshaped the entire solar system. The same gravitational chaos may have triggered a bombardment that scarred the moon, altered the planets, and changed the future of Earth itself. Others have suggested an even stranger possibility: that the missing planet never truly left, that it may still be orbiting the sun today, so distant and so cold that we have simply failed to find it. What makes the mystery difficult to ignore is that no one started by looking for a lost planet. The idea emerged because the solar system we observe today appears to carry the fingerprints of something that is no longer here. The surviving planets move through an arrangement that many simulations struggle to reproduce, unless an additional giant world once participated in the story. The planet is gone, but its absence may still be visible. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe, and we'll be here whenever you need a quiet journey through the cosmos. Let's start with a cloud of gas and dust that existed long before any planet called the solar system home. Long before there were planets, moons, oceans, or continents, there was only a drifting cloud. It stretched across an immense region of space, composed of gas, dust, and the scattered ingredients of future worlds. We can trace our own origins back to this place. Every rock beneath your feet, every planet in the night sky, and every atom within your body began as part of the same ancient reservoir. Around 4.6 billion years ago, something disturbed that cloud. Many planetary scientists suspect a nearby exploding star sent a powerful shock wave outward. As the wave passed through the solar nebula, gravity gained the upper hand. Regions of the cloud began collapsing inward. What had once been diffuse and spread across space started gathering into a denser structure. As the collapse accelerated, motion became increasingly important. A spinning cloud naturally flattens as it contracts, much like dough spreading beneath a rolling pin. Over time, the nebula transformed into a broad rotating disk. At its center, material accumulated rapidly, growing hotter and denser. There, the young sun began taking shape. The surrounding disk became a construction site on a scale almost beyond imagination. Tiny grains of dust collided constantly. Most impacts were gentle enough for particles to stick together. This process, called accretion, simply means growth through repeated accumulation. Grain joined grain, clumps joined larger clumps. Over millions of years, microscopic particles became objects measured in kilometers, which is about 0.62 miles. Growth accelerated. Bodies large enough to possess meaningful gravity began attracting surrounding material more effectively. These objects, known as planetesimals, became the foundation of future planets. They collided, merged, fragmented, and merged again. The disk grew crowded with developing worlds competing for the same resources. Distance from the sun determined what those worlds could become. Close to the center, temperatures remained too high for many volatile substances to freeze. Only dense rocky materials survived there, providing the raw ingredients for Mercury, Venus, Earth, and Mars. Farther out, conditions changed dramatically. Water, methane, ammonia, and other compounds could freeze into solid form. This boundary is often called the frost line, the region beyond which ices could contribute to planetary growth. That difference changed everything. Beyond the frost line, planetary cores accumulated mass far more efficiently. Some became enormous. Models suggest Jupiter's core formed in less than 1 million years, gathering material before the young sun's intense radiation dispersed much of the remaining gas. Vast envelopes of hydrogen and helium followed, creating the giant planets that would eventually dominate the outer solar system. By roughly 4.5 billion years ago, the major planets already existed, yet the arrangement would have looked unfamiliar to any observer watching from afar. The worlds were packed closer together, their orbits crossed gravitational pathways, momentum shifted constantly between neighboring giants. Stability had not yet arrived. What we see today feels orderly, but beneath that order lies evidence of an earlier age when the solar system was crowded, restless, and balanced on the edge of transformation. Imagine pausing the clock and looking back across the first few 100 million years of solar system history. You would recognize the young sun at the center, but much of the surrounding architecture would feel unfamiliar. The planets were present, yet they were travelers. Their modern addresses had not been assigned. Nothing stayed fixed. For much of the 20th century, astronomers assumed planets formed and remained roughly where we find them today. But as computer models improved, a different picture emerged. Gravity was constantly rearranging the system. Large worlds exchanged momentum with gas, dust, and smaller bodies, causing entire planets to drift across enormous distances. Jupiter appears to have been one of the most dramatic examples. Current models suggest it formed farther from the Sun than many early calculations assumed. After emerging as a giant world, Jupiter began moving inward through the surrounding disk of gas. This migration was gradual on human scales, yet immense in planetary terms. Over hundreds of thousands of years, Jupiter traveled toward the region where Mars now resides. Then the story changed direction. Saturn was forming behind it. As Saturn gained mass, the two giant planets became linked through a gravitational resonance, a condition where orbital periods settle into a repeating pattern. Their motions began influencing one another in a powerful and predictable rhythm. Instead of continuing inward, Jupiter reversed course. Saturn accompanied it. Planetary scientists call this scenario the Grand Tack hypothesis. The name comes from sailing. A sailing vessel changes direction by turning through the wind. Jupiter appears to have performed a similar maneuver, first moving inward, then sweeping back outward. You can think of it as a giant gravitational turn executed across millions of years. The consequences were profound. As Jupiter crossed regions rich in developing material, it scattered vast amounts of matter. Countless planetesimals were thrown into new trajectories. Others collided and broke apart. Some were expelled entirely. Areas that might have produced larger worlds were stripped of much of their building material. The asteroid belt bears the marks of this process. Evidence suggests it once contained far more mass than we observe today. After Jupiter's migration, only a tiny fraction remained. The modern belt is essentially a surviving remnant. Mars may also carry this history within its size. Compared with Earth and Venus, Mars appears unusually small. Models indicate that Jupiter's passage removed much of the material Mars would have needed to continue growing. The planet formed, but its development was interrupted before it could become something larger. Yet the outer regions were even less settled. Uranus and Neptune likely formed closer to the Sun than their present locations. Over hundreds of millions of years, interactions with surrounding material gradually pushed them outward. Their journeys reshaped distant regions and altered countless smaller objects along the way. When we reconstruct this era, we do not find a neat planetary system settling peacefully into place. We find motion, exchange, and continual rearrangement. The giant planets were still searching for stable paths, and every migration left gravitational consequences behind. By the time those movements began slowing, the solar system had become a far more crowded and unstable place than the orderly arrangement you see in the sky today. A change in scientific understanding sometimes begins with a telescope. Sometimes it begins with a spacecraft. In this case, it began with a problem. Planetary scientists kept finding pieces of the solar system that made sense individually, yet resisted fitting together into a single coherent history. The puzzle lingered for years. In 2005, a group of researchers working in the city of Nice, France, proposed a solution that would transform planetary science. Their work became known as the Nice model, named after the city where it was developed. Rather than treating the modern solar system as something that had always existed in its present form, the model suggested a dramatic reorganization occurred long after the planets formed. The timing was unexpected. According to the model, roughly 600 million to 700 million years after the solar system's birth, the outer planets entered a period of profound instability. Before that event, Jupiter, Saturn, Uranus, and Neptune occupied a far more compact arrangement. Their orbits sat closer together, creating a gravitational environment very different from the one we know today. Beyond the outermost planets stretched an enormous reservoir of icy debris. This region contained countless planetesimals, the leftover building blocks of planetary formation. The total mass of this distant population was far greater than the modern Kuiper belt that survives today. For a long time, the system remained relatively stable, but gravity is patient. As millions of years passed, Jupiter and Saturn gradually shifted into a specific orbital resonance. A resonance is a repeating gravitational relationship between orbiting bodies. In this case, Jupiter completed exactly 2 trips around the Sun for every one completed by Saturn. The pattern sounds orderly, yet its consequences were anything but. Energy began flowing through the system. Each orbital cycle reinforced the next. The resonance acted like a gravitational amplifier, steadily increasing instability among the giant planets. Small changes accumulated, orbits stretched and shifted, interactions grew stronger. Then the architecture began to unravel. Uranus and Neptune were scattered outward into the distant disk of icy objects. As they moved, they disrupted enormous numbers of planetesimals. Vast populations of frozen bodies were launched onto new trajectories. Some were thrown outward into deep space. Others traveled inward toward the terrestrial planets. The scars remain visible today. Mercury, Mars, and Earth's moon preserve evidence of a period known as the Late Heavy Bombardment. This term refers to an episode of intense impacts recorded across their ancient surfaces. The NICE model provided a mechanism capable of producing that surge of collisions while also explaining several unrelated mysteries at the same time. That was the remarkable part. The model reproduced the current positions of the giant planets. It helped explain the structure of the Kuiper belt. It accounted for Jupiter's Trojan asteroids, a population of objects sharing Jupiter's orbit. Multiple long-standing questions suddenly appeared connected by a single chain of events. But another pattern emerged as researchers repeated the simulations. Again and again, the calculations frequently worked best when an additional giant planet was present during the instability. And in many successful versions of the story, that extra world did not survive within the solar system at all. Scientific discoveries are often announced with photographs. A new planet appears in a telescope image. A galaxy emerges from darkness. A spacecraft sends back a remarkable view. The case for the lost giant planet is different. What researchers found was not a picture, it was a mismatch. The numbers refused to cooperate. When planetary scientists reconstructed the early solar system using only 4 giant planets, something consistently felt incomplete. The calculations could produce systems that resembled our own, but the success rate remained surprisingly low. Uranus and Neptune were especially troublesome. Their present orbits carried clues, suggesting a more complicated past than 4 giant worlds alone could easily explain. A missing participant seemed to linger in the mathematics. Researchers began testing alternative starting conditions. Instead of 4 giant planets, they inserted a fifth. The additional world was usually modeled as an ice giant, broadly similar to Uranus and Neptune. Such a planet would have contained large amounts of water, ammonia, and methane deep within its interior, wrapped beneath thick layers of hydrogen and helium. The results changed dramatically. When the fifth planet was eventually removed through gravitational ejection, the surviving planets often settled into arrangements strikingly similar to the solar system we observe today. Orbital distances matched more closely. Planetary motions aligned more naturally. Long-standing discrepancies became easier to resolve. The improvement was substantial. One of the most influential studies came from David Nesvorny of the Southwest Research Institute in Boulder, Colorado. In 2011, he published simulations examining different early solar system configurations. Systems that began with 5 giant planets reproduced the modern architecture of the solar system in roughly 35% of simulation runs. Comparable 4 planet models succeeded in fewer than 5% of cases. That difference drew attention. Researchers were not attempting to prove a lost planet existed. They were searching for configurations that generated realistic outcomes. Yet, the extra world kept appearing as part of the most successful solutions. The pattern emerged repeatedly across many independent calculations. The idea also addressed another puzzle. Uranus and Neptune are unusually large considering their current locations. Traditional growth models suggest building planets of that size so far from the Sun should have been difficult. Material becomes increasingly sparse with distance. Formation slows, but a more crowded outer solar system provides additional resources and more opportunities for planetary growth. The picture begins to fit together. Much of the foundation came from the work of Kevin Siganis, Rodney Gomes, Harold Levison, Alessandro Morbidelli, and other researchers associated with the development of the Nice model. Their simulations demonstrated how giant planets could exchange energy, migrate, and occasionally eject one another entirely. Today, the lost fifth giant is not viewed as an exotic speculation occupying the fringes of planetary science. It has become a serious and widely discussed possibility within mainstream theories of planetary formation. The evidence remains indirect. No telescope has ever seen the planet. Yet when scientists ask the solar system to explain itself, the answer repeatedly seems to include a world that is no longer here. Gravity often appears gentle from a distance. Planets circle stars. Moons circle planets. The motions seem orderly and dependable. Yet when massive worlds pass near one another, gravity becomes a mechanism of exchange, capable of rewriting entire planetary histories. This is where ejection begins. The process is known as gravitational scattering. The phrase sounds technical, but the idea is surprisingly straightforward. When two large bodies pass close together, they exchange momentum, which is the quantity that describes motion and speed. One object may lose orbital energy while the other gains it. Most encounters produce modest changes. Some do not. A giant planet moving through an unstable planetary system can repeatedly alter the paths of neighboring worlds. Each close approach shifts an orbit slightly. One encounter stretches it, another tilts it, a third changes its speed. The individual adjustments may seem small, yet gravity remembers every one of them. The effects accumulate. For the proposed fifth giant planet, the journey toward ejection was probably measured in millions of years rather than moments. It likely experienced dozens, perhaps even hundreds, of significant encounters while moving among the outer planets. Each interaction nudged it farther from stability. Every altered orbit increased the chances of another close passage. Eventually, one planet mattered more than all the others. Jupiter dominates the solar system gravitationally. Its mass exceeds the combined mass of every other planet by more than 2.5 times. When an object ventures near Jupiter, the exchange of momentum can become enormous. Space agencies routinely use this effect to accelerate spacecraft through gravity assist maneuvers. The same physics applies on planetary scales, only much larger. At the distance of Neptune, escaping the Sun requires a speed of roughly 4.2 kilometers per second, which is about 2.6 miles per second. A sufficiently close encounter with Jupiter can easily alter a world's velocity by more than that amount. Once the critical threshold is crossed, the orbit changes fundamentally. The geometry transforms. Instead of following a closed path around the Sun, the planet enters an escape trajectory. With every passing year, it travels farther away. Solar gravity continues pulling on it, yet the pull is no longer strong enough to reverse the motion. The world has effectively broken free. One boundary often used to describe this departure is the heliopause. This region marks where the outward influence of the Sun's solar wind yields to the surrounding interstellar environment. It lies roughly 100 astronomical units from the Sunday. By that distance, which is about 15 billion kilometers, which is about 9.3 billion miles, the lost planet would already be committed to its departure, but the consequences remained behind. Removing a giant planet changes the balance of the entire system. Every surviving world responds to the missing mass. Orbital distances shift, resonances weaken or disappear. New configurations emerge. The departing planet does not need to collide with anything. It does not need to fragment or burn away. It simply leaves, still intact, still carrying its atmosphere, and perhaps still accompanied by its moons as it begins the long passage beyond the Sun's domain. Picture the solar system at the instant balance began slipping away. No planet knew what was coming, of course. There was no signal, no warning, no visible marker announcing that one of the system's giant worlds was entering its final departure sequence. Yet gravity connected everything. Every orbit was part of the same conversation. Nothing moved alone. As the fifth giant planet drifted onto increasingly unstable paths, its gravitational influence continued reaching across enormous distances. Each pass altered the motions of neighboring worlds. By the time the planet approached ejection, The effects were no longer confined to the outer solar system. The disturbance had become system-wide. Even the young terrestrial planets responded. Proto-Earth, Proto-Venus, and Proto-Mars occupied a changing gravitational environment. Their orbital shapes, known as eccentricities, may have shifted slightly. Their orbital tilts, called inclinations, could also have been modified. The changes were not catastrophic. Planets were not thrown from the solar system, but small orbital adjustments can influence future evolution over immense spans of time. The asteroid belt felt the consequences more directly. This region had already endured earlier periods of disruption, but additional instability may have stirred surviving populations once again. Asteroids that had remained on relatively stable paths found themselves nudged into new trajectories. Some migrated inward, others collided. Fresh streams of debris began moving toward the inner planets. The timing is intriguing. Between roughly 4.1 billion and 3.8 billion years ago, the inner solar system experienced an extraordinary period of impacts. Planetary scientists call this episode the Late Heavy Bombardment. During this era, countless objects struck the Moon, Mercury, and Mars. Surface records from that period remain visible today. The Moon preserves the clearest archive. Unlike Earth, the Moon lacks active plate tectonics and widespread erosion. Ancient scars remain where they formed. Vast impact basins overlap one another across its surface, preserving evidence from an age of intense bombardment. When researchers examine those craters, they are effectively studying a geological record of gravitational upheaval. Earth's record is harder to read. Volcanism, erosion, and tectonic recycling have erased much of the evidence. Yet many scientists suspect our planet endured the same barrage. The traces may be fragmented, buried, or transformed beyond recognition, but the impacts themselves were likely unavoidable. Meanwhile, the giant planets continued rearranging themselves. Computer simulations frequently show Uranus and Neptune migrating into new positions during this chaotic period. In some cases, they even exchange places entirely before settling into the configuration we recognize today. Saturn's orbit shifts as well. The entire outer architecture evolves in response to the changing distribution of mass. By the end of the process, the solar system had acquired the structure familiar to us. The spacing of the planets, the arrangement of distant icy populations, and the orbital geometry stretching from Mercury to Neptune all emerged from this episode of instability. What appears orderly today may be the lasting imprint of a world that departed and carried part of the solar system's original design away with it. There was likely one orbit that mattered more than all the others. After millions of years of gravitational encounters, shifting trajectories, and mounting instability, the fifth giant planet may have found itself following a highly elongated path that carried it inward once again. This journey would not have looked unusual at first. The planet had crossed the outer solar system many times before. This passage was different. Its orbit had become increasingly stretched, bringing it into a dangerous relationship with Jupiter. Each revolution created another opportunity for a close encounter. Eventually, the geometry aligned. The giant world approached the solar system's most powerful planetary gravitational field, moving toward the moment that would determine its future. Distance mattered enormously. Planetary scientists cannot know the exact separation involved, but some simulations allow encounters occurring within only a few Jupiter radii. A planetary radius is simply the distance from a planet's center to its outer visible edge. At such proximity, gravity becomes intensely effective at exchanging momentum between large bodies. The transfer could be dramatic. Jupiter would not need to collide with the planet. Physical contact was unnecessary. Gravity alone could alter velocity enough to reshape the entire orbit. The encounter may have unfolded over only days or weeks, yet its consequences would last billions of years. The planet itself probably remained intact. On geological timescales, the event was surprisingly gentle. Strong tidal forces, which are stretching forces created by gravity acting differently across an object's diameter, may have heated parts of the planet's interior. Volcanic activity could have increased if solid layers existed within its structure. Internal stresses may have intensified, but there is no indication the world shattered or experienced catastrophic disruption. Its moons faced a greater risk. A close passage near Jupiter could have stripped away some of the smaller satellites orbiting the fifth planet. Moons that had circled their parent world for millions of years might suddenly find themselves captured by Jupiter instead. Once trapped, they would continue orbiting their new host along unusual paths. Some researchers find that possibility fascinating. As of 2024, Jupiter possesses 95 confirmed moons. Many are small, irregular objects moving on inclined and eccentric orbits. Such characteristics often suggest capture rather than local formation. It remains possible that a few originated elsewhere, perhaps accompanying a world that no longer belongs to the solar system. Meanwhile, the planet carried on. Its atmosphere would have changed very little during the encounter. If it resembled Uranus or Neptune, it likely remained dominated by hydrogen, helium, water, ammonia, and methane. Gravity altered the orbit. It did not rewrite the chemistry. Then came the departure. Within a few thousand years, the planet would have moved beyond the outer reaches of the solar system. The sun would grow steadily dimmer behind it. Familiar planets would fade into invisibility. Any surviving moons would continue circling their parent world as they crossed into interstellar space. From afar, nothing spectacular occurred. No explosion illuminated the darkness. No visible catastrophe marked the transition. A giant planet simply receded farther and farther away until it became another wandering world between the stars. Far beyond any map of the solar system, the lost planet continues its journey. Nothing about its motion suggests fragility. Worlds of this size are remarkably durable. They do not evaporate into space or slowly unravel with age. Billions of years after its departure, the planet is almost certainly still intact, carrying much of the same mass it possessed when it orbited the Sunday. But its appearance has changed. A planet receives enormous energy from a nearby star. Remove that source, and an entirely different environment emerges. Over immense spans of time, the lost world would have cooled steadily. Today, its temperature may hover near 10 Kelvin, which corresponds to roughly minus 263 degrees Celsius, or minus 441 degrees Fahrenheit. That is astonishingly cold. At temperatures like these, familiar gases behave very differently. Nitrogen and oxygen can condense into solid deposits. Material that once drifted through an atmosphere may settle onto the surface as frost or ice. Layers accumulate gradually, molecule by molecule. The chemistry evolves as well. While the planet orbited the sun, sunlight drove countless reactions in its upper atmosphere. Ultraviolet radiation continually broke apart molecules and allowed new compounds to form. In interstellar space, that source of energy is largely absent. Chemical pathways slow dramatically. Existing materials remain, but they interact in new ways. Methane persists. Ammonia remains. Both substances were likely abundant before the ejection and would still exist today. Yet without sustained illumination from a nearby star, the appearance of clouds, hazes, and atmospheric layers could differ significantly from anything we observe on Neptune or Uranus. Seeing the planet directly would be extraordinarily difficult. The world produces no visible light of its own. It reflects almost none because no nearby star illuminates it. Even the largest optical telescopes depend on light arriving from distant objects. A dark planet drifting between stars offers very little for those instruments to detect. Yet it may not be completely invisible. Deep inside the planet, radioactive elements continue releasing energy through natural decay. This process generates heat over immense periods. Giant planets can retain internal warmth for billions of years, long after external sources disappear. The lost world may therefore emit a faint glow in the infrared portion of the spectrum, which is a form of light associated with heat rather than visibility. The signal would be incredibly weak. At interstellar distances, detecting such radiation exceeds the capabilities of most current observatories. The planet could pass through the darkness entirely unnoticed, even while carrying a measurable source of internal energy. Any surviving moons would still accompany it. They would continue orbiting their parent world exactly as moons orbit planets throughout the universe. Together, they would form a miniature planetary system traveling through the galaxy. Their motions would remain governed by gravity, unchanged by the absence of a nearby star. And so, the planet moves onward. No neighboring worlds circle close by. No stellar sunrise marks the passage of time. Around it stretches the faint background glow left behind by the early universe itself. Within it lingers a dwindling reservoir of heat. Between those two sources of energy, a lost giant world continues drifting through the vast reaches between the stars. Distance becomes difficult to imagine once we leave the scale of planets. Even the vast spaces between Neptune and the nearest stars challenge intuition. Yet somewhere within those enormous expanses, the lost planet continues moving along a path established billions of years ago. The challenge is uncertainty. We do not know the exact direction of its departure. We do not know the precise speed it carried away from the Sunday. Those details vanished with the event itself. What we do have are computer simulations, and those simulations provide a range of possibilities. The numbers are staggering. Many models produce ejection velocities between roughly 5 kilometers per second, which is about 3.1 miles per second, and 20 kilometers per second, which is about 12.4 miles per second, relative to the Sunday. Such speeds may seem modest compared with light itself, yet given enough time they become extraordinary. Time changes everything. Over approximately 4 billion years of uninterrupted travel, a planet moving at those velocities could cover immense interstellar distances. Depending on the exact trajectory, the world may now lie anywhere from several light years away to hundreds of light years from its birthplace. The uncertainty is large because even tiny differences in speed become enormous differences after billions of years. Consider our nearest stellar neighbor. Proxima Centauri lies about 4.24 light years from the Sunday. If the lost planet followed a path through that region of space, it could have passed through Proxima Centauri's broader gravitational neighborhood long ago. It would not have stopped there. The planet was not searching for a destination. It was escaping one. Once an object exceeds solar escape velocity, its orbit fundamentally changes. Instead of remaining bound to the sun, it follows a hyperbolic trajectory, which is an open path that never loops back. Gravity from the sun weakens with distance, but it never completely disappears. The crucial difference is that it can no longer reverse the object's outward motion. The return journey is extraordinarily unlikely. For the planet to come back, another massive body would need to alter its motion significantly. Interstellar space contains stars, gas clouds, and drifting material, but the distances between major objects are immense. Direct gravitational encounters capable of reversing the planet's path are exceptionally rare. Meanwhile, the planet keeps moving. The interstellar medium, which is the thin mixture of gas and dust between stars, offers almost no resistance. At planetary scales, it functions as an almost perfect vacuum. There is essentially no friction to slow the world's progress. Its speed remains nearly unchanged. If the planet happens to reside within 100 light years of the Sun today, future observatories may eventually detect a faint infrared glow from its lingering internal heat, but that possibility remains speculative. We do not know where to look, and so the lost giant continues onward through the galaxy. Its direction remains unknown. Its destination is unknown as well. What is known is simpler. For billions of years, the planet has been moving away from the solar system at nearly the same speed, tracing a path that stretches ever farther into the darkness between the stars. A world wandering between the stars may sound extraordinary. Yet, as astronomers study the galaxy in greater detail, such objects appear less like exceptions and more like a vast hidden population. The galaxy may be crowded with them. For much of modern astronomy, planets were assumed to belong to stars. Every major example in our own experience followed that pattern. Worlds orbited suns, suns anchored planetary systems. The relationship seemed fundamental, but observations gradually revealed a different reality. Using a technique called gravitational microlensing, which detects objects through the bending of background starlight by gravity, astronomers have uncovered evidence for enormous numbers of free-floating planets. These worlds travel independently through interstellar space, unattached to any star. The numbers are astonishing. A study published during 2023 using observations from the Korea Microlensing Telescope network suggested there could be as many as 20 rogue planets for every star in the Milky Way. If that estimate proves accurate, our galaxy may contain more than 2 trillion wandering planets. Most remain unseen. Rogue planets appear across a remarkable range of sizes. Some possess masses smaller than Earth, others exceed Jupiter. The population spans nearly the entire known spectrum of planetary bodies. Their histories differ as well. Many likely began life within planetary systems. During periods of instability, close gravitational encounters scattered them outward until they escaped permanently. We have already followed one possible example from our own solar system, but countless others may have experienced similar departures around distant stars. Some may never have orbited a star at all. Dense pockets of gas can collapse directly under gravity. If the collapsing cloud gathers enough material, a star forms and nuclear fusion begins. If the mass remains below that threshold, a dark planetary object can emerge instead, sharing part of a star's origin story while never becoming a star itself. Several candidates already attract attention. One of the best known is a body called Canada-France Brown Dwarfs Survey Infrared 2149-0403. Estimates place its mass between roughly 4 and 7 times that of Jupiter. It resides about 100 light-years from our solar system and may represent a free-floating planetary object. Another candidate sits even closer. Wide Field Infrared Survey, Explorer 0855 -0.714, lies approximately 7.2 light years away. That makes it one of the nearest known isolated planetary or substellar objects beyond our solar system. Measurements suggest a temperature near -48 degrees Celsius or -54 degrees Fahrenheit, making it among the coldest known objects of its kind. Yet these discoveries likely reveal only a tiny fraction of what exists. Most rogue planets emit almost no visible light. They drift through regions where few stars illuminate them. Detecting such bodies requires patience, favorable geometry, and increasingly sensitive instruments. What does that tell us about our own lost planet? Its story becomes less unusual. Instead of being a solitary cosmic accident, it joins a vast population of wandering worlds scattered throughout the Milky Way. The darkness between stars is not empty. It is filled with planets that once belonged somewhere, and planets that may never have belonged anywhere at all. Across the battered face of the moon, an ancient record still survives. Long before continents drifted across Earth or oceans settled into familiar basins, countless impacts struck the inner solar system in a concentrated burst of violence that left marks still visible today. Astronomers call this period the Late Heavy Bombardment. Evidence points to a span between roughly 4.1 and 3.8 billion years ago. During that interval, impact rates increased dramatically. Vast numbers of asteroids and icy bodies crossed planetary orbits, colliding with worlds throughout the inner solar system. The moon preserves the clearest testimony. Unlike Earth, it lacks active plate tectonics, widespread erosion, and persistent oceans. Ancient scars remain exposed. Its highlands are packed with overlapping craters, layered so densely that newer impacts frequently cut through older ones. Looking across those landscapes is like reading a surviving archive from the solar system's earliest age. Important clues arrived during the 1970s. Samples returned by the Apollo missions were subjected to radiometric dating, a technique that determines age from radioactive decay. Many of the impact melt rocks clustered around the same period, close to 3.9 billion years ago. Rather than indicating a gradual decline in impacts after planetary formation, the results suggested a concentrated surge. A trigger was needed. This is where the planetary reorganization described by the NICE model becomes significant. As Uranus and Neptune moved outward through the primordial planetesimal disk, they disturbed enormous reservoirs of leftover material. A planetesimal is a small planetary building block left behind after major planets form. Billions of these icy objects occupied the outer regions of the solar system. Their orbits suddenly changed. Gravitational encounters scattered them across immense distances. Some were flung outward forever. Others fell inward toward the terrestrial planets. Earth, Mars, Mercury, and the Moon entered a prolonged shooting gallery of incoming debris. The consequences were immense. Certain impactors may have measured hundreds of kilometers across, which is about 62 miles. Collisions of that scale release extraordinary energy. Some models suggest repeated impacts could have vaporized large portions of Earth's oceans. Fresh crust would have melted. Atmospheres would have been reshaped. Conditions changed again and again. Yet destruction may not tell the entire story. Many researchers argue that incoming bodies carried water, carbon-based compounds, and complex organic molecules. These ingredients are central to biological chemistry. In that view, the same impacts that scarred planetary surfaces may also have delivered materials later used by life. But another possibility remains equally compelling. If primitive organisms had already emerged before the bombardment, Repeated giant impacts could have erased entire ecosystems. Heat, pressure, and global environmental disruption would have posed severe challenges to any early biosphere. The debate continues. Did life begin before this episode and survive it? Or did life emerge afterward from materials delivered during the bombardment itself? No definitive answer exists. The oldest evidence from Earth is difficult to interpret because geological activity has erased so much of the ancient record. What remains clear is the connection between planetary instability and Earth's story. The chain of events that reshaped the outer solar system and may have expelled a giant planet into interstellar space also altered the environment of our young world. The history of life and the history of planetary chaos became intertwined from the very beginning. Picture Earth at an age of only 450 million years. Oceans already covered much of the surface. Crust had formed and reformed. Chemical cycles were underway. In principle, conditions may already have supported the earliest microbial ecosystems. The timing is striking. Some of the oldest evidence connected to life comes from ancient zircon crystals discovered in Western Australia. Zircons are durable mineral grains that can survive immense spans of geological time. Certain carbon isotope signatures preserved within them have been interpreted as evidence for biological activity dating to roughly 4.1 billion years ago. That date sits near the beginning of the late heavy bombardment. Suddenly, two possibilities emerge. Perhaps life had already appeared and faced one of the greatest survival tests in planetary history. Or perhaps those early biological traces vanished during the bombardment, forcing life to begin again afterward. The distinction carries enormous implications for understanding how resilient life may be throughout the universe. Large impacts changed everything. Objects striking Earth during this era carried extraordinary kinetic energy. Kinetic energy is the energy of motion. Upon impact, that motion transformed into heat, shock waves, and global environmental disruption. Some simulations indicate that the largest collisions could have vaporized oceans, melted extensive portions of the crust, and raised surface temperatures to hundreds of degrees Celsius or hundreds of degrees Fahrenheit. Conditions became hostile. Any organisms living on exposed land or in shallow water would have faced severe challenges. Entire habitats could disappear within hours. Atmospheres would shift. Oceans would boil locally. Recovery might require immense stretches of time. But deeper environments tell a different story. Far below the surface, Earth possessed regions largely insulated from events occurring above. Hydrothermal vents, openings in the seafloor where heated water emerges from the planet's interior, may have offered refuge. These environments derive energy from chemical reactions rather than sunlight. Thick layers of water and rock could shield microbial communities from the worst effects of surface devastation. Many astrobiologists consider this possibility seriously. The concept is often described as a bottleneck. A bottleneck occurs when a population is reduced to a tiny surviving remnant that later expands again. In this scenario, life may have been compressed into scattered, protected habitats deep beneath oceans or underground. Most ecosystems could vanish while a few microscopic communities endured. Evidence supports the idea. Several models indicate that liquid water likely persisted in subsurface environments, even during intense bombardment phases. Deep fractures within the crust may have remained habitable. Hydrothermal systems may have continued operating. Pockets of stability could survive amid widespread planetary upheaval. This possibility leads back to the missing planet. The orbital instability associated with its ejection appears closely connected to the chain of events that triggered the bombardment. Without that instability, the flood of incoming objects may have been weaker or perhaps absent altogether. The environmental pressures shaping Earth's earliest biological history would have unfolded very differently. When you follow that connection to its conclusion, an extraordinary picture appears. The survival of life on Earth may be linked to a giant world that no longer belongs to our solar system. A planet expelled into interstellar space billions of years ago may have helped determine whether our earliest ancestors vanished forever or endured long enough for every living thing that followed. Far beyond Neptune, beyond the known planets and the familiar architecture of the solar system, a mystery may still be waiting. It does not reveal itself through reflected sunlight or direct observation. Instead, it announces its possible presence through gravity. Gravity leaves traces. In 2016, planetary scientists Konstantin Batygin and Mike Brown of the California Institute of Technology published a study proposing the existence of an undiscovered world in the distant outer solar system. Their argument did not begin with a telescope image, it began with a pattern. Several distant icy bodies appeared to be behaving strangely. These objects belong to a population known as trans-Neptunian objects, small worlds orbiting beyond Neptune. Their paths around the Sun showed an unusual alignment. Six of the most distant known examples possessed orbital characteristics clustered in ways that standard models struggled to explain through random chance alone. The numbers attracted attention. Calculations suggested the probability of such alignment occurring randomly was roughly 0.007%. That does not constitute proof, but it strongly implies that some unseen gravitational influence may be shaping their motions. A candidate soon emerged. The proposed object became known informally as Planet 9. Models suggest it could possess between 6 and 10 times Earth's mass. Its orbit may stretch across extraordinary distances, requiring somewhere between 10,000 and 20,000 years to complete a single revolution around the Sunday. Its location would be astonishing. Current estimates place it roughly 500 to 700 astronomical units from the Sunday. An astronomical unit is the average distance between Earth and the Sunday. At 700 astronomical units, the proposed planet would reside in a realm where sunlight is reduced to a faint glow. But another possibility deepens the mystery. Some researchers have suggested that Planet 9 and the lost fifth giant planet could be the same object. In this scenario, the planet avoided complete ejection during the chaos that reshaped the early solar system. Rather than escaping entirely, it was thrown onto an immense, elongated orbit that carried it to the outermost reaches of the Sun's gravitational domain. The distinction matters. A fully ejected planet becomes an interstellar wanderer. A planet on an extreme orbit remains bound to its star, even if it spends most of its existence far from the planetary family it once shared. The lost world would still belong to us, only barely. If that interpretation proves correct, the planet has spent roughly 4 billion years tracing a vast path through darkness, completing only a handful of orbits since the age when the major planets settled into their modern arrangement. Yet evidence remains indirect. Large surveys, including the Dark Energy Survey and observations conducted with the Subaru telescope and its Hyper-SuprimeCam instrument, have searched enormous portions of the sky without finding a confirmed planet. That absence has narrowed possible locations but has not eliminated the hypothesis. The search continues. A major advance may come from the Vera C. Rubin Observatory, expected to begin full scientific operations during the middle years of the 2020s. Its unprecedented survey of the sky may finally reveal whether an unseen giant still circles the Sunday, or whether the lost planet truly departed long ago. Astronomy often begins with light. We discover stars because they shine. We map galaxies because they glow. We study nebulae because their gases radiate across space. But some objects offer none of these advantages. They hide completely. A cold rogue planet, or a distant outer solar system planet, emits almost no visible light. It reflects very little sunlight and produces no fusion in its core. Against the immense darkness of space, such a world becomes extraordinarily difficult to find. Yet astronomers have learned to search indirectly. One of the most powerful methods is called gravitational microlensing. Microlensing occurs when an object passes between Earth and a distant background star. The gravity of the foreground object bends space itself, causing the starlight to brighten briefly. The effect may last only hours or days before disappearing. Then it is gone. The planet remains unseen, but its gravity leaves a measurable signature. By analyzing the timing and shape of that brightening event, researchers can estimate the mass of the hidden object and determine whether it may be a planet. Several projects specialize in this technique. The Korea Microlensing Telescope Network continuously monitors dense star fields, searching for these rare events. The optical gravitational lensing experiment has spent decades collecting similar observations. Together, they have transformed microlensing into one of the most productive tools for discovering wandering planets. But the future promises even greater sensitivity. The Nancy Grace Roman Space Telescope, currently scheduled for launch in 2027, is expected to detect hundreds of rogue planets through microlensing surveys. Some may possess masses similar to Earth. Others could approach the mass of Mars. Many would remain inaccessible through any other detection method. Another strategy focuses on heat. Even worlds drifting through darkness retain residual warmth from their formation and from radioactive processes within their interiors. That heat escapes as infrared radiation, a form of light beyond human vision. Instruments designed for infrared astronomy can sometimes detect these faint emissions. Progress has already begun. The James Webb Space Telescope has identified extremely cold brown dwarfs and several rogue planet candidates in nearby star-forming regions, but distance remains a formidable obstacle. A planet wandering dozens of light years away may radiate so little energy that even the most advanced instruments struggle to separate it from the cosmic background. Gravitational influence provides a third path. If Planet 9 exists, its presence should continue shaping the motions of distant trans-Neptunian objects. Every newly discovered object adds another clue. Each orbit helps astronomers narrow the regions of sky where an unseen planet could be hiding. The search area slowly shrinks. A major advance may come from the Vera C. Rubin Observatory and its legacy survey of space and time. This project will repeatedly map enormous portions of the sky, cataloging billions of objects and tracking subtle motions across many years. The outcome may arrive surprisingly soon. Within the next decade or two, astronomers may finally detect a hidden giant lingering at the edge of the solar system. If no evidence emerges after increasingly comprehensive surveys, the case for a nearby survivor will weaken dramatically. Either way, the hunt is entering its most revealing era. Across the galaxy, planetary systems rarely remain exactly as they formed. Worlds migrate, orbits stretch and tilt, gravitational relationships shift over millions of years. When we look outward at other stars, we find growing evidence that planetary loss is not unusual. It may be expected. One intriguing example lies around the star known as HR 8799, located about 133 light-years from Earth. This young system contains 4 giant planets that have been directly imaged, allowing astronomers to observe the planets themselves rather than infer their existence indirectly. Their arrangement appears stable today, yet many dynamical simulations, meaning calculations that track how gravity changes motion over time, suggest that such systems can become unstable as ages pass. A crowded system rarely remains crowded forever. Small gravitational exchanges accumulate gradually. One orbit shifts slightly, another stretches. Eventually, a close encounter may occur. When that happens, one planet can gain energy while another loses it. Over long enough timescales, a world may be expelled entirely. Evidence for similar events appears elsewhere. The system called Upsilon Andromedae contains planets whose orbital inclinations, meaning the angles of their paths around the star, are difficult to explain through calm evolution alone. Researchers have proposed that an additional planet once occupied the system. Its gravitational interactions disrupted the architecture before the missing world was ultimately thrown away. The survivor planets still preserve the memory. Wider patterns reinforce the same conclusion. Studies of binary star systems, where two stars orbit each other, reveal planetary arrangements that often bear the fingerprints of earlier instability. Computer models repeatedly reproduce the observed structures only after including episodes of planetary scattering and ejection. The process appears common. Even stranger histories emerge around millisecond pulsars, rapidly rotating stellar remnants left behind after massive stars die. Pulsar timing, which measures tiny changes in the arrival of radio pulses, has revealed planets orbiting some of these extreme objects. Their origins remain debated. Some may have survived catastrophic stellar explosions. Others may have formed later or been captured from elsewhere. Each possibility reflects a turbulent past. Large statistical surveys strengthen the broader picture. Observations from the Kepler Space Telescope uncovered thousands of planets and hundreds of multi-planet systems. When astronomers compare their spacing and orbital arrangements with theoretical models, many systems appear consistent with earlier periods of instability. Missing worlds leave traces. Certain gaps between planets seem wider than expected. Some orbital patterns suggest former neighbors no longer present. Although direct proof remains difficult, the collective evidence points toward planetary removal as a recurring outcome of system evolution. What we see around other stars increasingly mirrors the story reconstructed for our own neighborhood. Gravity builds planetary systems, but gravity also reshapes them. It removes worlds as readily as it creates stable configurations. Throughout cosmic history, countless planets have likely been scattered into darkness between the stars. Seen from that perspective, the lost fifth giant of our solar system becomes less extraordinary. It becomes part of a vast galactic pattern, repeated again and again across billions of planetary systems, wherever gravity gathers worlds and allows them to compete for space. At the center of this story sits a world so massive that every major orbit in the solar system has felt its influence. Long before any planet was lost, Jupiter already dominated the gravitational landscape around it. Nothing else came close. Jupiter contains roughly 318 times the mass of Earth. More striking still, it holds more than twice the combined mass of every other planet orbiting the Sunday. When astronomers model the long-term evolution of planetary systems, Jupiter often emerges as the primary architect of change. Its reach extends everywhere. Gravity weakens with distance, yet Jupiter's enormous mass allows it to shape the motions of asteroids, comets, and planets across vast regions of space. A small adjustment during a close encounter can eventually grow into a completely different orbit millions of years later. The effects accumulate. One of the clearest demonstrations arrived in 1994. A comet known as Shoemaker, Levy 9, wandered too close to Jupiter. Powerful tidal forces, meaning gravitational forces that vary across an object's length, pulled the comet apart into multiple fragments. Over 6 days, more than 20 pieces slammed into Jupiter's atmosphere. The impacts were extraordinary. Dark scars larger than Earth spread across the cloud tops. For the first time, humanity watched a major collision unfold elsewhere in the solar system. Jupiter had intercepted an incoming object and absorbed the consequences itself. That protective role remains important. Many comets entering the outer solar system encounter Jupiter before reaching the inner planets. Some are captured, others are redirected. A number are expelled entirely. Through these interactions, Jupiter reduces certain impact risks faced by Earth. But protection tells only part of the story. The same gravity that removes dangerous objects can also accelerate them. During close approaches, Jupiter functions as a gravitational slingshot. Spacecraft use this effect deliberately, stealing a tiny amount of orbital energy to increase speed. Natural objects experience the same process. So do planets. Within the framework of the Nice model, repeated encounters between Jupiter and the fifth giant gradually increased the smaller world's orbital energy. Each pass altered its trajectory. Each interaction pushed it closer to escape. Eventually, one encounter crossed a critical threshold. The final departure followed. Calculations suggest that Jupiter was probably the last major planet to interact with the fifth giant before its removal from the solar system. No collision occurred, no explosion followed. Gravity alone completed the process. Yet, some simulations reveal an even stranger possibility. Under slightly different conditions, Jupiter itself can become unstable during these early rearrangements. In a small number of model runs, Jupiter experiences strong scattering events that threaten its own long-term position. The ejection of the fifth giant helps dissipate excess energy and allows the surviving system to settle. A different outcome would have reshaped everything. Without Jupiter occupying its present orbit, the asteroid belt could have retained far more material. Impact rates on the inner planets may have remained elevated for much longer periods. Earth's geological and biological history could have unfolded along a very different path. When we trace the chain of events backward, the pattern becomes difficult to ignore. Jupiter remained. Another giant departed. The architecture surrounding us emerged from that exchange, leaving one planet behind to govern the solar system and another to wander among the stars. Scattered among the outer planets are dozens of small worlds whose histories remain frustratingly incomplete. They circle giant planets faithfully, yet many seem oddly out of place. Their orbits differ. Their inclinations vary. Their paths hint at origins elsewhere. Some may be relics. As the lost fifth giant approached its final encounter with Jupiter, gravity would have acted on more than the planet alone. Any moons traveling around that world would have entered the encounter as well. During an extremely close passage, competing gravitational forces could have disrupted those ancient relationships. The consequences would have been complex. A moon orbiting comfortably around the fifth planet might suddenly find itself pulled by Jupiter's enormous gravity. Some moons could remain bound to their parent planet. Others might be flung outward into independent solar orbits. A few may have become trapped around Jupiter itself. Capture is difficult. A passing object usually carries too much energy to remain permanently bound. Yet in chaotic multi-body interactions, where several gravitational influences operate simultaneously, energy can be exchanged in unexpected ways. Under the right conditions, a former moon can lose enough orbital energy to become a permanent satellite of another planet. Jupiter possesses many candidates. As of recent counts, Jupiter hosts 95 confirmed moons. Only a handful are large spherical worlds like Io, Europa, Ganymede, and Callisto. Most are tiny, irregular bodies following elongated, tilted, and often retrograde paths. Retrograde means they orbit opposite the planet's rotation. That behavior raises questions. Moons that form naturally around a growing planet usually share similar orbital directions and relatively orderly paths. Many of Jupiter's irregular satellites violate those expectations. Their unusual motions suggest capture rather than local formation. Patterns emerge within the chaos. Astronomers divide many of these objects into orbital families, including the Himalaya group, the Ananke group, the Carme group, and the Pasiphae group. Members within each family share similar trajectories, implying that larger captured bodies may have fragmented long ago. But what were those larger bodies? One possibility is that some originated far from Jupiter and were later captured independently. Another possibility connects them to ancient planetary instability. If the fifth giant carried its own collection of moons, a close encounter could have stripped away portions of that system and distributed them around Jupiter. The idea remains speculative. No individual moon can currently be traced with certainty to a lost planet. Too much time has passed, too many collisions, and orbital changes have occurred. Yet the hypothesis remains physically plausible and consistent with known gravitational processes. Saturn presents additional clues. Its moon Phoebe follows a retrograde orbit and possesses characteristics unlike Saturn's major moons. Observations indicate that Phoebe likely formed elsewhere in the outer solar system before being captured. Its existence demonstrates that giant planets can acquire foreign satellites. The outer solar system preserves these records imperfectly. Worlds change, orbits evolve, evidence fades, yet some traces endure across billions of years. If even a few irregular moons once belonged to the fifth giant, fragments of that vanished planetary system still circle the planets that remained behind. Every observation becomes more personal. When astronomers measure the composition, motion, and history of these distant moons, they may be studying the surviving companions of a world that departed long ago, leaving only scattered attendants to mark its former place among the planets. Imagine turning away from the lost planet itself and looking instead toward the worlds that may have accompanied it. The question of life begins there, because an ice giant offers few obvious places for biology to gain a foothold. The planet itself was likely inhospitable. If it resembled Neptune or Uranus, most of its mass would have consisted of hydrogen, helium, water, methane, and ammonia. Beneath thick atmospheric layers, pressure rises to extraordinary levels. Temperatures increase. Density changes. No known environment within such a planet resembles the stable surface conditions associated with life on Earth. But moons change the picture. Throughout the solar system, some of the most promising locations for extraterrestrial biology are not planets at all. They are satellites orbiting giant worlds. These moons demonstrate that habitability can emerge in places once considered unlikely. Saturn's moon Titan provides one example. A dense atmosphere surrounds Titan. Lakes and seas of liquid methane spread across its surface. Beneath an icy shell, evidence suggests the existence of a buried ocean of liquid water. Energy sources, complex chemistry, and long term stability make Titan an object of enormous scientific interest. Jupiter's moon Europa offers another path. Observations indicate that Europa contains a global ocean hidden beneath ice. Tidal heating, meaning internal warming generated by gravitational flexing, prevents that water from freezing solid. The ocean may contain more water than all of Earth's oceans combined. That possibility matters here. If the fifth giant possessed a system of large moons, some may have experienced similar conditions. Gravitational interactions between a giant planet and its satellites can generate internal heat for immense spans of time. Rock and ice are squeezed repeatedly as orbits evolve. The resulting friction produces warmth. Warmth can preserve oceans. Liquid water trapped beneath thick ice remains protected from radiation, impacts, and harsh surface conditions. Hydrothermal activity on the seafloor could provide additional chemical energy. Such environments are considered among the strongest candidates for supporting microbial ecosystems beyond Earth. No evidence exists that this happened, yet the ingredients may have been present. The story becomes even more intriguing after the ejection. A moon surviving alongside the departing planet would carry its internal ocean into interstellar space. The parent planet would no longer orbit a star. Sunlight would disappear. Surface temperatures would steadily decline. But deep beneath the ice, change would arrive more slowly. Subsurface oceans contain enormous amounts of thermal energy. Ice shells act as insulation. Even as tidal heating gradually weakens and orbital relationships stabilize, liquid water could persist for extraordinarily long periods. Models suggest hundreds of millions of years are possible. During that interval, an ocean hidden beneath kilometers of ice could remain active while the surrounding planetary system drifted between the stars. The surface would grow darker and colder, yet conditions below might remain comparatively stable. A remarkable possibility emerges. If life ever arose within such an ocean, it would not depend on sunlight. It would not see stars. It would exist beneath layers of ice, orbiting a wandering giant planet long after that world had left its birthplace behind. The fifth planet may never have hosted life. Even so, the environments surrounding it remind us that habitability is broader than it first appears. Sometimes, the most promising refuge is not a planet at all, but a hidden ocean carried through the darkness by a moon that refused to freeze. Step back for a moment from the history of our own planetary family. As the scale expands, the disappearance of a single world begins to look less like an exception and more like a recurring consequence of gravity itself. Planetary systems are born crowded. Young stars emerge, surrounded by disks of gas, dust, rock, and ice. From that material, planets assemble in large numbers. Many never remain where they formed. Gravitational interactions begin immediately, with each world tugging on its neighbors through millions of years of orbital evolution. Some systems find balance, many do not. A gravitational instability occurs when planetary orbits begin exchanging energy in ways that amplify over time. Small disturbances grow larger. Orbital paths cross. Close encounters become inevitable. Once that process starts, one outcome appears repeatedly in computer simulations. A planet gets expelled. The more planets a system contains, the greater the opportunity for destabilizing encounters. Massive worlds are especially effective at scattering smaller companions. In many simulations of planetary formation, one two, or even three planets are removed before a stable arrangement finally emerges. This appears to be common. The implication becomes extraordinary when applied across an entire galaxy. The Milky Way contains an estimated 100 billion to 400 billion stars. Even conservative assumptions produce staggering numbers. If each planetary system ejects only one world on average, hundreds of billions of rogue planets would exist. But current estimates reach higher. Observations using gravitational microlensing, a technique that detects objects through the bending of background starlight, suggest that free-floating planets may number in the trillions when smaller bodies are included. Mars-sized worlds, Earth-sized worlds, and giant planets all contribute to that unseen population. Most will never be observed directly. They move independently through the galaxy, following paths established billions of years ago. Some pass near stars, others travel through sparse regions between stellar systems. A few may eventually experience another close gravitational encounter and become captured by a new host star. That possibility remains rare. Many will continue alone for periods longer than the current age of Earth. Their geology may continue beneath frozen surfaces. Internal radioactive decay can provide heat for immense spans of time. Moons may remain in orbit. Subsurface oceans could persist in select circumstances. Entire histories unfold unseen. What does the galaxy actually contain beyond the stars we recognize? The answer may include countless planetary stories that no longer possess a sun to illuminate them. Gravity writes those stories everywhere. Worlds form, orbits shift, systems reorganize. Some planets remain, others depart. The process emerges naturally from the same physical laws operating around every young star. Seen from that perspective, the lost fifth giant of our own solar system becomes part of a much larger pattern. Its journey is neither unique nor improbable. Across the Milky Way, countless planets have already taken the same path, leaving their birth systems behind and joining an immense population of wandering worlds moving through the darkness between the stars. A brief flash across the sky changed the way astronomers think about the boundaries of planetary systems. Until recently, interstellar objects existed largely as theoretical expectations. We assumed material must travel between the stars. Yet, no visitor from another stellar system had ever been confirmed. That changed in October of 2017. Astronomers using the Panoramic Survey Telescope and Rapid Response System in Hawaii detected a faint object moving through the inner solar system on a trajectory unlike anything previously observed. Calculations quickly revealed a remarkable fact. The object was not orbiting the Sunday. It had arrived from elsewhere. Named one Oumuamua, meaning scout or messenger from afar arriving first, the object entered the solar system at tremendous speed and followed a path that could not be explained as a long-period comet returning from the distant outskirts of our own planetary system. Its orbit was hyperbolic, meaning it possessed enough velocity to escape the sun entirely. The visitor was passing through. Observations soon deepened the mystery. Estimates suggested an unusually elongated shape, perhaps approaching a ratio of 10 to 1 between length and width. No visible coma appeared around it. No tail emerged. Yet precise measurements revealed a small additional acceleration as it departed, an effect that standard gravity alone could not fully explain. Debate followed. Researchers proposed several possibilities, including hidden outgassing, unusual geometry, or exotic surface properties. Years later, no single explanation commands universal agreement. But the most important conclusion remained unchanged. Interstellar objects are real. Then another arrived. In November of 2019, astronomers detected two I Borisov. Unlike Oumuamua, Borisov looked far more familiar. It displayed the characteristics expected of a comet, including visible activity produced by volatile materials escaping into space. Its orbit left no doubt about its origin. This object also came from another stellar system. The galaxy had provided a second confirmation. For you and me, these discoveries carry a deeper implication. Material does not remain confined to the place where it formed. Small bodies travel between stars. Dust travels between stars. Fragments of planets and moons travel between stars. The exchange never stops. If our lost fifth giant shed debris during gravitational encounters long ago, some of that material may have wandered through distant planetary systems across billions of years. Tiny remnants from our solar system could already reside around stars whose names we have never spoken. But the exchange works both ways. As the ejected planet crossed the galaxy, it may have entered the gravitational neighborhoods of other stars. Most encounters would have been distant and uneventful. A few may have subtly altered its path. Passing clouds of interstellar dust and debris could have contributed material to any surviving moons that accompanied it. Nothing travels in complete isolation. Oumuamua reminded astronomers of a reality that is easy to overlook when studying maps of planetary systems. The borders we draw around stars are conveniences, not barriers. Objects move. Gravity reaches outward. Paths overlap across immense spans of time. The solar system is part of a larger galactic environment, and somewhere within that environment, the lost planet continues its journey through a universe where worlds, fragments, and wanderers pass endlessly from one stellar story into another. Imagine opening a window across centuries and inviting three of history's greatest astronomers to examine the modern picture of our solar system. The conversation would begin with recognition. Planets still circle the Sunday, gravity still governs motion, the familiar architecture remains. Yet almost immediately, the discussion would drift into territory none of them could have anticipated. Tycho Brahe spent his life measuring the heavens with extraordinary precision. In 1672, he observed a brilliant new star, what we now recognize as a supernova. Its appearance challenged a belief that had endured for generations, the idea that the celestial realm was permanent and unchanging. The sky had changed. For Brahe, that realization was revolutionary, yet even he still lived within a worldview that imagined the solar system as a largely stable structure. Planets moved according to observable patterns. Their arrangement seemed enduring. Johannes Kepler inherited Brahe's observations and transformed them into something profound. Working through years of calculation, he derived the laws of planetary motion during the early 17th century. These laws described how planets travel around the sun in elliptical paths and how their speeds change along those paths. The mathematics was beautiful, but Kepler's equations described the solar system as he found it. They did not reveal the distant past. They offered no glimpse of migrating giants, destabilized orbits, or vanished worlds. To Kepler, the planetary arrangement reflected a deeper harmony woven into creation. Then came Isaac Newton. In 1687, Newton published the law of universal gravitation, providing the mathematical framework that eventually allowed scientists to model planetary interactions across immense spans of time. Every modern simulation tracing the fate of a lost planet rests upon principles Newton established. Yet Newton faced a troubling problem. When he considered multiple planets pulling on one another over enormous durations, he struggled to explain how perfect stability could persist indefinitely. He suspected that occasional divine intervention might be necessary to preserve order. The long term consequences of countless gravitational interactions remained beyond calculation. The calculations were impossible then. Modern researchers approach the same problem differently. Instead of solving every interaction by hand, they use numerical simulations, computational models that calculate gravitational forces repeatedly across billions of years. An n-body simulation, meaning a calculation that tracks many interacting objects simultaneously, can reveal behaviors too complex for direct mathematical solutions. Those tools emerged only during the late 20th century. With powerful computers, astronomers discovered that planetary systems are often dynamic rather than permanent. Worlds migrate, resonances shift, orbits become unstable. Entire planets can be expelled into interstellar space. This realization would have seemed astonishing to Brahe, Kepler, and Newton. But each generation inherits a larger universe than the one before it. Brahe learned that the heavens could change. Kepler learned that celestial motion followed discoverable laws. Newton revealed the force governing those motions. Modern astronomy added deep time, computation, and planetary evolution. The result is a cosmos far less static than our ancestors imagined, a place where even a planet can disappear, leaving only subtle traces behind for future minds to uncover. Somewhere beneath every story of wandering planets and vanished worlds lies a deeper layer, one built entirely from mathematics. Long before a simulation produces an ejection, before a planet changes course, before a system settles into stability, gravity follows rules that are exact and unforgiving. Nothing is random. When planetary scientists reconstruct the early solar system, they rely on what are called n-body simulations. An n-body simulation is a computational model that calculates the gravitational pull between many objects at the same time. Every planet influences every other planet. Every small change creates another change. The calculations multiply rapidly. The complexity becomes immense. A single simulation begins with an assumed arrangement of planets orbiting a young sunday. Researchers then allow the system to evolve according to the laws of gravity. Millions of virtual years pass, then hundreds of millions, sometimes billions. At the end, scientists compare the result with the solar system we observe today. Most attempts fail. Planets collide. Orbits become distorted. Giant worlds drift into positions that do not match reality. Entire systems fall apart. These failed outcomes are valuable because they reveal which starting conditions could never have produced the architecture surrounding us now. This process became central to the work of David Nesvorny at the Southwest Research Institute. He tested thousands of possible early solar system configurations. Each run asked the same question: could a compact arrangement of giant planets naturally evolve into the planetary system we see today? The answer carried a surprise. Models beginning with only 4 giant planets struggled to reproduce the present solar system. Successful outcomes occurred in fewer than roughly 5% of simulation runs. But when a 5th giant planet was added to the starting configuration, the success rate increased dramatically, rising to roughly 35%. The difference was striking. A 5th planet acted as a source of instability that ultimately created stability. Through a sequence of gravitational encounters, one giant world departed while the survivors settled into orbits closely resembling those observed today. But these results are not speculative mathematics detached from reality. The same gravitational equations used in these simulations guide spacecraft through the solar system with remarkable accuracy. Mission planners calculate trajectories using the identical physical laws. Tiny course corrections can place robotic explorers within distances measured in meters after journeys lasting years. The mathematics is trusted daily. Consider the Voyager spacecraft. Decades after launch, they continue moving through the outer reaches of the solar system. Voyager 1 is now more than 23 billion kilometers from Earth, which is about 14 billion 300 million miles. Its position can still be predicted using gravitational physics developed across centuries of scientific work. Those equations remain consistent everywhere. When applied to the early solar system, they repeatedly point toward the same conclusion. The most successful reconstructions often require a giant planet that no longer remains among the survivors. Different simulations vary in detail. Individual histories change, yet a common pattern appears again and again. Something departed. The evidence does not emerge from a crater, a telescope image, or a fossil remnant. It emerges from mathematics itself, a language describing motion with such precision that a missing planet leaves an imprint long after the planet is gone. There is a natural temptation to imagine a reunion. After following the trail of a vanished world across billions of years, you might wonder whether gravity could someday reverse the story. Could the lost planet curve back toward home and reappear among the familiar worlds it left behind? The mathematics offers a clear answer. Almost certainly not. When a planet gains enough speed to exceed the sun's escape velocity, it crosses an important boundary. Escape velocity is the minimum speed required to permanently overcome a body's gravitational pull. Once that threshold is passed, the planet is no longer traveling on a closed orbit. Its path becomes hyperbolic, an open trajectory that carries it away without returning. The departure is decisive. Gravity from the sun never disappears. Even at enormous distances, the sun continues to tug on the planet, but the pull weakens with distance, while the planet retains enough momentum to continue outward. The result is a permanent escape rather than a temporary excursion. Space itself offers no rescue. Between the stars lies the interstellar medium, a thin mixture of gas and dust spread across immense distances. Yet this material is extraordinarily sparse. A planet moving through it encounters almost no resistance. There is no atmospheric drag, no ocean of particles, no natural braking system capable of slowing a giant world enough to recapture it. The journey continues. For the lost planet to return, another gravitational encounter would need to intervene. Passing near a star could alter its trajectory. A sufficiently close approach might steal some of the planet's orbital energy and redirect its motion. In theory, repeated encounters could even send it back toward the region where it originated. But theory is not probability. Stars appear crowded when we look at the night sky, yet the actual distances between them are vast. Even the nearest stars are separated by trillions upon trillions of kilometers. Over 4 billion years of travel, the lost planet may pass through numerous stellar neighborhoods, but the chance of experiencing the precise close encounter required for a return remains extraordinarily small. The galaxy is mostly emptiness. Still, cosmic conditions will not remain unchanged forever. Several billion years from now, the Milky Way and the Andromeda Galaxy are expected to merge. During that long interaction, stellar motions will become more complicated. Some regions of the merged galaxy may briefly contain higher concentrations of stars. Rogue planets wandering through those regions could experience more gravitational encounters than they do today. Yet, even then, certainty remains elusive. A redirected trajectory would not guarantee a homecoming. The planet could be scattered toward another region entirely, captured by a different star, or sent deeper into intergalactic space. Gravity creates possibilities, not promises. So, on every human timescale, and on every timescale relevant to the present solar system, the conclusion remains unchanged. The planet is gone. Its departure represents one of nature's most final acts. A gravitational ejection does not leave scars that heal or paths that naturally retrace themselves. Once the escape occurs, the cosmos simply keeps moving forward, carrying the traveler farther into the darkness with every passing year. Sometimes the most important influence on a system is the thing that is no longer there. A missing planet sounds like an absence, a gap in the story. Yet, as we follow the consequences of its departure, that absence begins to look more like a turning point. The solar system that surrounds us today is remarkably stable. For roughly 4 billion years, the giant planets have occupied orbits that change only gradually. Jupiter remains distant from Saturn. Uranus and Neptune continue their slow journeys through the outer darkness. Their gravitational relationships fluctuate, but they do so within boundaries that preserve the overall architecture of the system. That stability matters deeply. Life requires time. Oceans need ages to circulate. Continents need ages to drift. Evolution needs immense spans of uninterrupted history. A planetary system undergoing repeated episodes of major orbital instability would make those long intervals difficult to sustain. But stability was not guaranteed. The early solar system appears to have been far more crowded and dynamic. Giant planets interacted strongly with one another. Small changes in orbital energy accumulated over millions of years. Eventually, one world was expelled, and the surviving planets settled into a configuration capable of enduring across geological timescales. The consequences reached inward. Earth follows a nearly circular orbit around the Sunday. Because of that shape, the amount of solar energy received through the year remains relatively consistent. Seasonal changes occur, yet they remain within limits that have allowed liquid water to persist across vast stretches of time. A more chaotic planetary arrangement might have produced something very different. Repeated disturbances from migrating giant planets could have altered the paths of the inner worlds. Orbital eccentricity, meaning how stretched an orbit becomes, might have increased. Climate patterns could have experienced dramatic shifts. Long periods of environmental stability might have become far less common, but the effects may extend beyond orbital geometry. Many researchers suspect that part of Earth's water inventory arrived from icy bodies originating in the outer solar system. During the era of intense bombardment that followed planetary reorganization, comets and water-rich objects were scattered inward. Some collided with Earth, others struck neighboring worlds. Those impacts carried ingredients. Water, organic compounds, and other volatile materials became incorporated into the young planet. Debate continues regarding exactly how much water arrived this way, yet the connection between outer solar system material and Earth's development remains an important area of research. The moon also occupies a special place in this story. Its gravitational influence helps regulate Earth's axial tilt, reducing extreme variations over long periods. That contribution supports climate stability. The Moon formed earlier through a separate event, yet its continued partnership with Earth unfolded within the stable environment that emerged afterward. Everything became connected. A giant planet arrived. It survived for hundreds of millions of years. Gravitational encounters followed. One world departed. The remaining planets settled. Water reached Earth. Long-term stability emerged. Geological history unfolded. Life endured. But viewed from enough distance, the sequence forms a single chain. The lost planet did not leave an empty space behind. Its departure helped create the conditions under which every ocean, every ecosystem, and every living thing on Earth could eventually exist. Across the Milky Way, countless stars are older than our own. Around many of them, planets formed long before Earth existed. If those systems followed the same gravitational rules we have been exploring, then many experienced their own eras of instability, migration, and planetary loss. The pattern should be common. Every young planetary system begins as a crowded environment. Worlds emerge from disks of gas and dust. Orbits shift. Gravitational interactions accumulate. Some planets survive in stable arrangements, while others are scattered outward or removed entirely. The process appears woven into planetary formation itself. If intelligent life exists elsewhere, many civilizations may have arisen only after such upheavals ended. Imagine looking upward from another inhabited world. The planets visible in that sky might represent only the survivors of a much larger family. Ancient worlds may have vanished billions of years before the first living organisms appeared. Entire chapters of planetary history could be absent from direct observation, preserved only in orbital clues and mathematical reconstruction. The realization would carry weight. Humanity once believed Earth occupied the center of creation. Later, we learned that our planet circles an ordinary star. Discovering a lost planet forced another adjustment in perspective. For an alien civilization, uncovering evidence that several worlds had disappeared before its own emergence could produce a similarly profound transformation in how it understands cosmic history. But the implications extend beyond philosophy. Researchers involved in the search for extraterrestrial intelligence have traditionally focused on detecting artificial radio transmissions. Those searches remain important. Yet some scientists have suggested looking for different signatures, particularly in infrared wavelengths, which are forms of light associated with heat. The reasoning is intriguing. A rogue planet wandering through interstellar space receives little energy from any star. If an advanced civilization somehow existed there, survival would require alternative energy sources. Nuclear reactions, geothermal heat, or other technologies might generate detectable warmth. Such activity could potentially create unusual infrared signals distinguishable from natural planetary cooling. No evidence has been found. Still, the idea rests on known physics rather than fantasy. Rogue planets exist. Internal heat exists. Technological civilizations remain a possibility. Combining those facts creates a legitimate scientific question, even if the answer remains unknown. Some thinkers have gone further. The physicist Freeman Dyson considered whether extremely advanced societies might one day reshape entire planetary systems. Among the more speculative proposals was the concept of a nomadic planet civilization, a society intentionally traveling through interstellar space aboard a world detached from its parent star. Such concepts remain far beyond current capabilities, but they emerge from the same reality that produced our own missing planet. Gravity can move worlds. It can rearrange systems. Under the right circumstances, it can send planets into the darkness between stars. That possibility changes how we view permanence. From the surface of Earth, the heavens often appear fixed and enduring, yet deeper investigation reveals continual motion. Stars orbit galaxies, galaxies interact, planets migrate. Some remain bound to their suns, others depart forever. Our lost planet belongs to that larger story. It reminds us that cosmic architecture is not carved in stone. Across the galaxy, countless civilizations, if they exist, may be descendants of systems whose histories were shaped by worlds that stayed, worlds that collided, and worlds that drifted away. There is a strange simplicity to the moment a planet leaves a solar system. No blaze marks the event. No cosmic alarm sounds across the darkness. The change occurs through motion alone, through gravity doing exactly what gravity has always done. For hundreds of millions of years, the fifth planet belonged here. It formed alongside the worlds we know today. The same rotating cloud that produced Earth, Jupiter, Saturn, Uranus, and Neptune also gathered material into this lost giant. It shared the same beginning. It participated in the same evolving architecture. Its gravity helped shape neighboring orbits as the young solar system settled into form. Then the encounters began. One close pass altered another orbit. A later interaction changed it again. Tiny differences accumulated across immense spans of time. None of those moments required destruction. None required impact. The process unfolded through ordinary gravitational exchanges, each one redirecting momentum from one world to another. But accumulation has consequences. Eventually, the planet crossed a boundary defined by mathematics. Its speed became great enough to escape the sun's gravitational hold. At that instant, the relationship changed forever. The planet remained physically intact, yet its future no longer belonged to the solar system that created it. It kept moving. From a distance, nothing dramatic would have appeared. The giant world would still circle through darkness with its clouds, its internal heat, and perhaps its moons. But each passing year increased the separation. Every orbit carried the remaining planets forward together, while the fifth giant drifted farther beyond their reach. The departure was permanent. That permanence gives the story unusual weight. Many cosmic events involve transformation. Stars explode and create new elements. Galaxies merge into larger structures. Even collisions can build new worlds from debris. Gravitational ejection follows a different path. Something remains whole while losing its place within the system that once defined it. But the planet itself experiences nothing. It possesses no awareness of exile, no understanding of departure. It is matter following physical law. Rock, ice, gas, and gravity continue their interaction exactly as before. The emotional meaning exists only in the minds of observers who reconstruct the event billions of years later. Even so, the image lingers. A world that once occupied a position among familiar planets now travels through regions so distant that present instruments cannot locate it. If moons accompanied that journey, they traveled as well. If rings existed, they traveled too. Entire landscapes may still exist around a planet that no longer has a home star. What does belonging mean on cosmic scales? The question emerges naturally from the physics. Planetary systems appear stable when viewed across human lifetimes. Yet stability often represents a temporary arrangement within a much longer story. Orbits evolve, configurations shift, relationships between worlds change. Our solar system reflects only the latest chapter. The arrangement we inherited feels permanent because it has endured for billions of years, but beneath that appearance lies a deeper truth. The system surrounding us today is not the system that first emerged from the solar nebula. It is the version that remained after one world departed and the others stayed behind. Across the history of Earth, countless species have lived and vanished without ever knowing where they were. Forests spread and retreated, oceans opened and closed. Entire branches of life flourished for millions of years beneath a sky whose deeper history remained unknown. Then something changed. A species emerged that could ask how the solar system came to be. Over generations, we learned to measure planetary motion, calculate gravitational forces, and reconstruct events that occurred billions of years before the first human walked the Earth. From scattered clues, we pieced together a story no creature before us had ever imagined. We became historians of worlds. The scientists who developed the NICE model did not discover the lost planet by seeing it directly. They followed evidence preserved in orbital architecture. They built simulations. They tested possibilities. They compared outcomes. Through mathematics and computation, they traced the surviving planets backward into a far more crowded past. But that achievement depended on conditions that existed long before humanity. Every observatory, every university, every scientific tradition arose on a planet that remained habitable across immense spans of time. Complex life required stability. Intelligence required continuity. Civilization required an environment capable of sustaining generation after generation without catastrophic disruption of Earth's orbit. The chain runs deep. A rearrangement among giant planets billions of years ago helped establish the gravitational structure we see today. Once the outer solar system settled into its long-term configuration, Earth occupied an environment that remained comparatively stable through the rise of oceans, continents, ecosystems, and eventually conscious observers. But the connection is more direct than it first appears. Had the giant planets continued migrating dramatically over geological timescales, the inner solar system could have experienced repeated orbital disturbances. Changes in Earth's path around the Sun might have altered climate patterns on scales hostile to long-term biological development. The conditions that allowed evolution to unfold gradually may never have persisted. Instead, stability followed. Life adapted, complexity increased, brains evolved, language emerged, knowledge accumulated. From that progression came astronomy, mathematics, and the ability to investigate events that occurred before Earth possessed even its earliest microbial ecosystems. The irony is remarkable. The same gravitational episode that scattered planets, redirected countless objects, and transformed the architecture of the solar system also helped create the conditions necessary for future observers to understand what happened. A moment of instability contributed to billions of years of relative order. You and I are part of that outcome. Every city ever built, every scientific theory, every piece of music, literature, engineering, and art emerged from a chain of causes extending back through planetary history. Remove enough links from that chain, and the world we know never appears. This is not symbolism. It is the consequence of physical events unfolding across deep time. Gravity altered orbits, orbits influenced environments, environments shaped evolutionary possibilities. Evolution eventually produced minds capable of looking backward through history. The lost planet never intended any of this. It possessed no awareness of future oceans, future forests, or future civilizations, yet its departure became one element in the sequence that allowed all of them to exist. Long before humanity appeared, a giant world left the solar system, and the path it cleared became part of the story that ultimately led to us. A surprising amount of this story remains unfinished even now. We stand at a moment when new instruments are arriving faster than ever before, each designed to reveal objects that previous generations could barely imagine detecting. The search is accelerating. Across mountaintops, deserts, and orbital observatories, astronomers are preparing surveys that will transform our inventory of the solar system. For decades, many distant objects remained invisible simply because they were too faint, too small, or too far away to appear in existing datasets. That limitation is beginning to fade. One of the most important developments comes from the Vera C. Rubin Observatory. Its legacy survey of space and time will repeatedly scan the sky over many years, creating an unprecedented record of moving objects. Every sweep adds information. Every newly discovered body becomes another clue. But the significance reaches beyond simple discovery. The suspected influence of Planet 9 rests partly on patterns seen among distant trans-Neptunian objects, a population of icy bodies orbiting far beyond Neptune. As Rubin identifies many more of these objects, astronomers will gain a much larger sample. Statistical uncertainty will shrink. Some patterns may grow stronger, others may disappear. The outcome matters. If the clustering remains consistent as discoveries increase, the argument for a massive unseen world becomes considerably stronger. But if the distribution spreads into randomness, one of the central pieces of evidence weakens substantially. Each new object contributes to the test. Another powerful tool is approaching. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will conduct the most sensitive gravitational microlensing survey yet attempted. Gravitational microlensing occurs when an object's gravity briefly magnifies the light of a distant star. The technique can reveal bodies that emit little or no light of their own. That includes rogue planets. Astronomers expect the survey to detect large numbers of wandering worlds, potentially including objects comparable in mass to Earth and Mars. Every detection improves our understanding of how often planetary ejections occur and how many worlds travel between the stars. Meanwhile, the James Webb Space Telescope continues examining cold and distant objects with remarkable sensitivity. Although designed primarily for many different scientific goals, its observations contribute to a broader picture of planetary formation and evolution throughout the galaxy. The evidence keeps accumulating. Suppose Planet 9 is eventually found. The discovery would rank among the most significant in modern astronomy, the first confirmed new planet in the solar system since Neptune was identified in the 19th century. Models of solar system history would gain powerful support. But another possibility remains. Extensive searches may ultimately fail to find such a world. If that happens, astronomers will need to reconsider why distant objects appear arranged as they do. The mystery would not vanish, it would deepen. Either result reshapes our understanding. We may discover a hidden planet, or we may learn that the traces left by the lost world are subtler than expected. In both cases, the next 20 years promise a clearer view of the place we call home and the history written into its architecture. Beyond every planet we can name, beyond every orbit we have mapped, there may be a traveler still carrying the memory of this system in its motion alone. We cannot point to it. We cannot measure its present location. Yet the possibility remains, drifting through the background of everything we have explored. Somewhere in the galaxy, a world perhaps comparable to Neptune may still be moving through interstellar space. It would have begun its existence here, within the same swirling cloud of gas and dust that produced the sun, the planets, the asteroids, and eventually the ground beneath you. Its origins were shared long before Earth carried oceans filled with life, before continents assembled and separated, before any creature looked upward at the night sky. That distant world occupied a place among the giants. Its gravity participated in the architecture of the young solar system. It influenced neighboring orbits. It helped shape the pathways along which countless smaller bodies traveled. Then the arrangement changed. Gravity does not require intention. It follows only its own rules. Through repeated encounters among massive worlds, energy was exchanged. Orbits shifted. Distances grew. At some point, the departing planet crossed a boundary from which return became extraordinarily unlikely. Nothing dramatic appeared in the sky. No explosion announced the moment. No cosmic flash marked the transition. The planet simply continued onward until the sun's gravitational hold weakened below the threshold needed to keep it bound. From that moment forward, its path belonged to the wider galaxy. The journey never stopped. For roughly 4 billion years, it may have continued through regions between the stars, carrying whatever moons survived and enduring conditions colder than almost anything found within the planetary system it left behind. Star after star would pass at immense distances. Entire constellations would change. Galaxies would continue their slow evolution. Still it moves. We believe such a world may exist because the evidence left behind points toward it. Again and again, planetary scientists construct simulations of the early solar system. Again and again, a recurring pattern emerges. A fifth giant planet appears. A fifth giant planet departs. The resulting arrangement closely resembles the system we observe today. The absence has structure. We have never photographed this object. We do not know its appearance. We cannot say whether it possessed moons with buried oceans or landscapes hidden beneath layers of ice. Those details remain beyond reach. What remains accessible is the imprint left on everything that stayed behind. That imprint includes us. The stable planetary arrangement that followed helped create conditions under which Earth could remain habitable across immense stretches of time. Oceans persisted, life endured, intelligence emerged. Eventually, a species evolved capable of reconstructing events that occurred billions of years before its own existence. And so, the question remains. Perhaps the lost planet is still traveling tonight through the darkness between stars. Perhaps it always will. Yet, even at an unimaginable distance, it remains connected to this story because the world you inhabit was shaped partly by the space it left behind.